Welcome back. We will continue our discussion, brief overview of convergence of random variables. Yesterday we defined three different notions of convergence of random variables. The first is convergence with probability 1 or convergence almost surely, which is the same thing, which says that the sequence xn of random variables, you look at the set of omegas for which the sequence xn of omega converges to x of omega. All right. So, for each little omega, xn of omega is a sequence of real numbers, right, and x of omega is a real number, right. So, you just test whether xn of omega for that particular omega converges to x of omega, all right. So, if it does converge, you put that omega into one bucket, right, and if it does not converge to x of omega, you put the omega into some other bucket, right. Now, xn, you say that this xn converges to x almost surely if the bucket where the convergence does take place has probability 1, okay, and the bucket where the convergence does not take place has probability 0. So, that is almost sure convergence. Convergence with convergence in probability, which is definition 2 here, is a little weaker. You may not immediately see that it is weaker. It only concerns itself about the behavior of the probability at n. Okay. So, you look at the probability that the difference between xn and x, the absolute difference between xn and x exceeds some epsilon. You choose any epsilon, 10 to the minus 6, 10 to the minus 8, whatever you want, and you look at the probability that xn minus x exceeds epsilon. Okay. So, this is some p n epsilon. So, for a fixed epsilon, this is a sequence of probabilities in n, and you want this probability sequence of probabilities to go to 0. Okay. So, in the second definition, it is the sequence of probabilities that is converging to 0, as opposed to the sequence of random variables themselves which are converging in the definition 1. Okay. And finally, definition 3 talks about convergence in distribution. So, you look at that CDF of the nth random variable f x n, okay, and you send n to infinity and you see if this converges to f x, x is the proposed limit. And you look at the you look at, for let us say you fix a little x for one thing. So, you fix a little x and you send n to infinity and look at whether f x n of x converges to f x of f x, right. And if this happens for all little x wherever so for all little x wherever f x is continuous, where the limiting distribution is continuous, then you say x n converges to x n distribution. Okay. So, these three are the most commonly used and they are progressively weaker. Okay, this can be shown. So, convergence almost surely is the strongest notion, followed by convergence in probability, then followed by convergence in distribution. So, convergence almost surely implies convergence in probability, which implies convergence in distribution, but none of the reverse implications are true. Okay. So, just if you have not seen this thoroughly before, you can view it. So, there is the lectures 43 through 45 on of the course probability foundations, which I recorded about 5 years ago. This has this in much more detail. Okay. So, this is also on YouTube, and you can look at these 3 lectures if you want to learn more about these notions of convergence. In fact, you can watch it. I think I suggest you watch it anyway, because it is a good review for you. Now, so maybe I should give you some examples to illustrate these convergence notions. See, the most well known result, perhaps the most important result of almost sure convergence is, you know what it is the strong law of large numbers. Okay. There is a strong law of large numbers which basically says that sample averages converges to the expected value almost surely. Okay. So, that is an example of almost sure convergence. There is also a weak law which says the sample average converges in probability to the sample mean. Convergence in distribution, you know, what is the most famous result in convergence in distribution? central limit theorem, right. Central limit theorem we might have studied, right. So let me just recap this. So, this is lecture 3, right. This is module 3. Yeah, okay, lecture 3. Is that okay? No, bigger? Large numbers, right, large. Laws of large numbers and central limit theorem, let us see, right. There is a strong law of large numbers. We basically take a sequence of random variables xi, let this be, let independent and identically distributed random variables with expected value of xi equal to some x bar. Let us say this is presumed to be finite. Okay. Define the sample average Sn over n as sum over xi I is equal to 1 to n over n. Okay. This is the sample average. So, you know what IID is independent identically distributed. So, you have a sequence of random variables which all have the same, all come from the same distribution. Okay, the marginal distributions are the same and they are independent. Okay. So, all finite order joint CDFs will factorize into product of the marginals. Okay. So, you know what that means, and you are assuming that the each of these expected value of xi is equal to some x bar, okay, and this has to be finite. And then you generate a million IID samples of these random variables xi, and you take the sample average, you sum all of them and divide by the number of samples. Okay. So, this laws of large number just generally deal with the sample average getting close in some sense to the so called ensemble average, which is the expected value, right. So, strong law of large numbers says that say then Sn over n converges to x bar almost surely. Okay. This is the strong law of large numbers. Okay. Sample average converges to the expected value of each of these random variables almost surely. So, again what does this mean? So whenever, so let us say for some, so for a particular omega, right, let us say you fix omega in omega. So, you have a real sequence x1 of omega, x2 of omega dot dot dot, right, and from this you can calculate Sn of omega over n, right. So, each of these xi of omega you can add till n xn of omega sum by n, right, divided by Sn of omega over omega. So, for each omega you get this sequence Sn over n of omega, right. Again you make different buckets, okay. You test whether Sn of omega for that particular omega, you test whether Sn of omega over n converges to the number x bar is just a number, right. Sn of omega over n is a sequence of real numbers because you are fixing little omega, right. So, if Sn of omega over n converges to x bar, you put that omega in one bucket. Sorry, x bar is a number. See, each of these xi's are IID, right. So, expected value of xi is some number, some finite number we are assuming, right. If it is infinity, this is not true. The expected value of a random variable can be infinite or even undefined, right. In those cases, law of large number does not hold. Okay. Strong law holds if the expected, actually it holds necessary and sufficient condition for strong law to hold is if expected value of absolute xi is finite. Okay. All right. So, it is not, so you can look at it as x bar of omega, right. So, normally the limit is also a random variable, but here the limit is a number. You can view the limit also as a random variable which is always constant, it is a constant random variable, so to speak, correct. Maybe that is your confusion, right. Usually xn converges almost surely to some other random variable, here the limit random variable is just a number which is x bar. Okay. So, yeah, so you collect those omegas where this convergence to x bar happens, and you can collect those omegas where this Sn of omega over n may not even converge, right, may not converge to anything, right, or it may converge to something which is not x bar. So, in those cases you put it in a different bucket. What strong law is saying is that the probability measure of the omegas where Sn of omega over n converges to the expected value x bar is 1. Okay. That is what this is saying. So, this is slightly non-trivial, it is not a very trivial result to prove, okay, and this result is altogether only about 100 years old. Okay. This was proved much after the measure theoretic machinery was brought into probability theory. Okay. Whereas the weak law of large numbers, under the same conditions, it says that Sn over n goes to x bar in probability. Okay. So, meaning that, so this is just the same as saying if you send limit n tending to infinity, probability of, if you look at that guy, Sn over n minus x bar greater than epsilon, this limit is equal to 0 for all epsilon greater than 0. Okay. So, what this means is that you take a very large n and look at Sn over n. Okay. The probability that the sample average deviates from x bar by more than epsilon goes to 0 as n becomes larger and larger. Okay. Of course, you already know that almost sure convergence implies convergence in probability. So, you may ask what is special, right. There is nothing really special about the weak law, in fact, it is contained in the strong law, but the weak law is about 300 years old, it is easier to prove and easier to visualize, and even people with undergraduate students, for example, who do not have measure theoretic background can understand what this means, but you know, strong law is a little harder to digest, right. It is a stronger result, but it is harder for students to digest, and it took people longer time to figure out that it is even true. Okay. I hope you appreciate the difference between these two. Okay. So, maybe I should illustrate with one picture. So, perhaps I will just draw a picture to illustrate what I am talking about. So, let us say this is my n, okay. Okay, and for a particular omega I am going to plot Sn over n. Okay. So, what we are saying, so for some large n, let us say let me give myself, let us say this is my let us say that is my x bar, okay, and I am going to give myself a an epsilon band, Okay. So, I am going to look at so that is my epsilon band okay, around, so that width is epsilon. So, I am giving myself an epsilon band around the true mean x bar okay, and I am looking at what S n over n is actually doing. Okay. So, weak law is basically has to do with fixing some large n. Okay. You will fix some large, let us say you fix some large n is equal to n naught, let us say it is large, and you look at the probability that S n over n falls outside this band at n, right, at n naught, right. You look at the probability that S n over n falls outside the epsilon band. Okay. So, what it is saying is that what weak law is saying is that the probability of S n over n falling outside this epsilon band becomes smaller and smaller and as n becomes large. Okay. Is that clear? So, if you were to plot the CDF of S n over n for large n, right, you fix an n naught, right, you plot the CDF of S n over n, it will be much of the probability will be concentrated around x bar, right. So, the CDF will rise very sharply at x bar, right. So, if I were to plot, so this is what weak law is saying, right. So, if I were to plot, this is a different plot. So, you look at whether S n over n is falling within the epsilon band or not for that n naught. So, you fix n naught and look at S n naught over n naught, sorry, this is the CDF of x, okay, the CDF of, you are fixing n naught and looking at the CDF of S n naught over S n naught over n naught. So, that is x bar. So, the CDF will look, so it will remain quite flat and then suddenly take off very quickly and then reach 1. Okay. So, essentially if you look at that epsilon band around, so this is your epsilon band around your sample mean, much of the probability will be concentrated around this sample mean, okay, and the probability outside this band will be very small, okay, and as n becomes larger and larger, it becomes smaller and smaller and goes to 0. This is what weak law is saying, okay. This is an illustration for weak law, okay, whereas strong law concerns itself with the convergence of the entire sequence S n over n. Okay. So, weak law only looks at a particular n, right, fix an n and you look at the CDF of S n over n, the probability that it deviates from x bar by epsilon, right, whereas you look at for strong law you are looking at the entire sequence, right. So, for different values of n, so let me plot with let us say this blue color. So, S n for n is equal to 10, it may be here, right. So, whatever, right, 100. So, this sequence jumps around, let us say this is a particular omega, right, this corresponds to a particular omega, right. So, it may jump around a bit, sort of gets closer, right, may jump around, but at some point the entire sequence. So, if you look at any n naught, there exists an n naught beyond which the entire sequence gets constrained to an epsilon band. You fix whatever epsilon you want, the sequence S n, this is some particular omega, all right, this blue crosses correspond to the sample averages of some particular little omega. Of course, if you have a different little omega, you will get different places for these crosses, right. However, what we are saying is that on a set of probability 1, right, these little omegas on a set of probability 1, these crosses will be constrained to an epsilon band beyond some n naught, never to ever get out, okay. It will never get out beyond some n naught, okay. Weak law is only looking at a particular n, right, and looking at the probability that you go outside this band, but strong law is looking at the behavior of the entire sequence S n over n for n greater than or equal to some n naught, okay. So, the entire sequence converges to x bar, that is what this is saying, right. So, the entire sequence gets within an epsilon, never to get out, okay. So, in some sense you can, so this is an illustration for strong law, okay. So, in some sense you can say that strong law has to do with the entire behavior for large n, right. The sequence itself constrains itself to it will always be within the epsilon band around x bar for large enough n, right, beyond some n, whereas for weak law we are only looking at a particular n, okay.
Sir, in weak law of large numbers, can I choose some other n naught and then can I go on picking some other n naught and say this is holding true?
Well, yeah, I mean the weak law holds for a particular n naught, right. The probability that your sample mean deviates from x bar by more than any epsilon goes to 0, okay. But strong law says that not just at n naught, at n naught and beyond n naught, the entire sequence of your sample mean will lie within an epsilon band, okay. So, it will for any epsilon, okay. So, this is convergence of the sequence itself, okay. So, maybe I will just give you see this strong law and weak law, I mean they are both true, right, but maybe it is a little, it is a perhaps a better idea to illustrate with a sequence of random variables which converges almost surely, which converges in probability, but not converge almost surely, okay. So, there you can find an example like that. So, here both convergences are true. So, let me give you an example. Excuse me. So, you take another example. Let xi be independent. So, you have independent random variables such that probability that x n is equal to 1 is 1 over n and probability that x n is equal to 0 is equal to 1 minus 1 over n, okay. So, x n's are a sequence of independent random variables, okay, such that the nth random variable is 1 with probability 1 by n, okay. So, this is an example, this is different from strong, I am done talking about laws of large numbers, okay. I am giving you a different example just to illustrate the conceptual difference. So, in this example, so the 100th random variable is 1 with probability 1 over 100, correct. So, as you go farther and farther, it is more and more likely to be 0, right. So, the millionth random variable will be 1 with probability 10 power minus 6 and 0 with probability 1 minus 10 power minus 6, right. So, here this is an example where x n converges to 0 in probability, but you can argue that x n does not converge to 0 almost surely, does not happen, okay. So, to see that sorry, yeah, so that is where I am coming to. So, you can argue that x n converges to 0 in probability, right. Why? It is because if you look at this, right, limit n tends to infinity, probability that absolute value of x n minus limit is 0, right, the proposed limit is 0 greater than epsilon. This is what you have to look at, right. What is the probability that absolute x n is greater than epsilon? Yeah, say what values does x n take? 1 or 0, right. So, if it is bigger than epsilon, then yeah, so it has to be 1, right. So, this probability is simply limit n tending to infinity 1 over n, which is 0, right. So, you have convergence in probability, correct, but you can argue that x n does not converge to 0 almost surely. Okay. However, x n does not converge to 0 almost surely. Okay. To see this, well, one easy way to see this is to invoke Borel-Cantelli lemma, okay, which I suppose some of you have studied, right. If you have not studied, again I suggest you go and look it up somewhere, right. So, this comes from the fact that x n does not converge to 0 almost surely comes from Borel-Cantelli lemma. One easy way to see it is Borel-Cantelli lemma, or you can also make some first principle argument, it is not difficult. So, the essence is that although there are this x n is overwhelmingly likely to be 0, what happens in this case is that if you fix some large n, you are guaranteed to have some occasional 1 beyond that n. Okay. With probability 1, there will be infinitely many 1s popping up, okay, even though they are becoming increasingly rare. You can show using Borel-Cantelli lemma that there are infinitely many 1s in this sequence, the sequence of x n's. Okay. Since there are infinitely many 1s with probability 1, this x n cannot go to 0 almost surely, right, because this 1 keeps popping up once, very rarely, but it still keeps popping up. Okay. So, if x n probability x n equal to 1 was 1 by n square, then you can argue using Borel-Cantelli lemma that x n will also go to 0 almost surely. Okay. So, if you have not seen Borel-Cantelli lemma, I suggest you go take a look at it. Okay. It is a cute result. Okay. So, this is an example to really appreciate the difference between these two. Okay. So, this almost sure convergence looks at the convergence of the entire sequence, and this sequence, although most of the entries are 0, there will be occasionally 1s popping up. So, the sequence does not converge to 0. Okay. So, this is a good illustration of this phenomenon. Okay. So, this module is finished.